Good evening, everyone. I'm Ryuichi from Tokyo Institute of Technology. Today, I introduce a new force sensor that estimates force from shape deformation. So let's begin with social background. There are growing interest in the approach known as computer-patient reading (AAL). AAL focuses on solving problems by altering the environment rather than relying on individuals. And this approach is significant for elderly because physical function of elderly declines day by day, and it is challenging to modify their physical function. So support from the environment is necessary. By sensing elderly and analyzing it, we can provide tailored support to individuals. However, to obtain force data, we have to aim force sensor to the environment or via wearable device. Using this conventional method, it is hard to set up a measurement environment. Regarding the technical background, I introduce three advantages of computer vision. First, progress in computer vision allows us to obtain various image features. For example, Meta released their latest segmentation model that makes it easy to extract shape features from images. And second, the progress in computer vision, progress in machine learning allows us to make predictions based on image input. For example, convolutional neural network enable variety of tasks with image input, such as image recognition or posture recognition. And finally, regarding the acquisition of image data, many affordable RGB-D devices are available using this. So this technical advancement offers a new way of estimating force only by observing deformation. So in the future, we believe we can sensorize by only deformation observation. There are three advantages of new sensor based on deformation observation. First, it offers low installation cost. You can measure with just a camera. There are minimum or no need for additional cost. And second, it provides greater flexibility in measurement environment. So changing the measurement location or measurement target is very easy. And third, it expands the measurement range. Unlike the conventional embedded or wearable device, all the entire area captured by the camera is a target for measurement. However, accuracy is still unclear. So in this study, we propose a new force sensor principle based on deformation and verify its accuracy. This is an overview of this research. First, we extract deformation feature by image processing. Then create a feature and force data set. And finally, run relationships using convolutional neural network. However, to achieve this challenging task, it is important to start with simple problems. So at the very first experiment, we create a FEM dataset composed of noise-free or ideal features. Through this problem, we confirm the principle of estimating from deformation. In this problem, we deform these numbers shaped objects using external force. And then we verify if we can estimate external force distribution and position from information on the shape deformation. So I explain how to create FEM dataset. We created FEM dataset for the program using Abacus CAE. And first, we create 10 models to resembling number 0 to 9. And then we deform each of them with a row of different position and different magnitude. By doing so, we created 12,800 datasets. This is an example of FEM dataset. The input data consists of three elements: deformed shape, original shape, and contact point. All of these elements are labeled with 0 and 1. 0 means no material, and 1 means material. And in label data, the values are attached to a pixel where the force exists. And this is an overview of a force sensing model. For CNN architecture, we adapt encoder-decoder model, which is typically used for computer vision. Then we create original dataset and narrow down the area of force. And next, I explain evaluation function. In this study, we use mean squared error and mean relative error. For training, we use MSE as a loss function, and for evaluation, we use MSE and MRE. And that is the model's predicted value and ground truth value. When calculating this evaluation function, the error between these images are accumulated along with the pixels. And this is a figure of FM dataset results. On the left side are the ground model's prediction, while on the right side are the ground truth. As you can see in the top two figure, no large error was observed in position and magnitude. So it indicates that model can generalize for unknown roles. Additionally, in case where the error is relatively large, there's almost no big difference. This is a numerical result. As you can see in the table, we succeed in predicting the force with 6% of MRA on this data. So through such problem, we confirm the principle of sensing by deformation. So our next step is more practical experiments, including actual image processing. So first, we extract deformation feature by image processing, and then to create dataset, we combine this feature and sensor value together. And finally, a relationship using convolutional neural network. By including this actual image processing, we apply the method to more realistic situations. And this is a method of creating datasets by integrating image processing and sensor data. The first, we extract shape by using superpicture and clustering to RGB image. And then we extract human labels by semantic segmentation and define the common position between human labels and shape as the contact position. So finally, by extracting the position of sensor value, we get the force image, which serves as level data. By doing so, we create 7,315 sets of datasets. This is a figure of shear dataset results. Similar to the toy problem, on the left side are the model's prediction, while on the right side are the ground truth. In many cases, as you can see in the top figure, the force distribution was predicted at the correct location and magnitude. However, in some cases, we noticed that the force is predicted where it doesn't exist, or small noise occur in some pixels. Here's the numerical result. The MRE was 90% on testing data. And the error of 90% is a bit higher compared to the super precise measurement like this type of load cell. However, it is within acceptable margin for the pressure sensor like this. This is the limitation and feature of in this study. The first, we have some room for improving accuracy. The error was 90% in realistic data. At this level of error, it is hard to use for super precise measurement. However, increasing the dataset size may lead to improvement. So we would like to examine the possibility of controlling accuracy by adjusting the dataset size. And second, dealing with occlusion is also challenging task. To address this, by introduction of existing occlusion handling modules or a combination of multi-camera is promising. And finally, extension to 3D object is necessary. We believe by using RGB-D camera, we can extend this method to full 3D object. In conclusion, we propose a novel sensing technology that estimates force by deformation. And we achieved an accuracy of 6% under ideal condition and 90% under realistic condition. I think this research shows the possibility of centralization of everything in everyday life setting. Thank you for your attention.